So welcome back, my dear students. Last class we have discussed on the failure of bolted connections and how to determine the strength of a bolted connection. So today's class we are going to see some of the numericals associated with the design of a bolted connection. Mainly the first type will be how to find the strength of a bolt. The second type will be how to find the efficiency of a bolted connection, and the third one will be the design of a bolted connection. So we will start with the strength determination of a bolted connection. So see this question. The question says determine the strength of a 20 mm diameter bolt of grade 4.6 for the following cases. First one is lap joint, then single cover butt joint with 10 mm thick cover plate, double cover butt joint with 8 mm thick cover plate. The main plates to be joined are 14 mm thick. Use Fe 410 grade steel. So here at the beginning you need to understand certain things. The first one is it is given the grade of the bolt is 4.6. The ultimate strength of the bolt, I could say, as Fu is equal to, if it is 4.6, then 4 into 100 Newton per mm square, that is 400 Newton per mm square will be the ultimate strength of the bolt, and the yield strength Fy of the bolt will be this 400 into, there is one 4.6, that it is 400 into 0.6, this grade 4.6, it is 0.6 Newton per mm square, and that value is 240 Newton per mm square. So if it is grade of the bolt is given as 4.6, which means the ultimate strength is 4 into 100 Newton per mm square, and yield is 400 into 0.6 Newton per mm square. If it is 4.8, then the ultimate is 400 Newton per mm square, and Fy is 400 into 0.8. It goes like that. Now it is given use Fe 410 grade steel. So Fe 410 grade steel means the material used for the plate is Fe 410 grade steel. So Fe 410 grade steel means the ultimate strength of the plate is 410 Newton per mm, and for Fe 410 grade steel the ultimate is 410 Newton per mm square, and the yield strength of the plate is 250 Newton per mm. So this tells about the bolt, and this tells about the plate used. Now given in the question, it is given determine the strength of the 20 mm diameter bolt. You are asked to determine the strength of the bolt. So there might be two types of question. That is, first one is to determine the strength of bolt. So the strength of the bolt is the least value of shear strength of bolt, bearing strength of bolt. It is the least value of shear strength of the bolt or bearing strength of the bolt. If it is asked to determine the shear strength of the strength of the bolt. If it is asked to determine the strength of the joint, it is least value of either shear strength of the bolt, shear strength of the bolt, or bearing strength of bolt, or tensile strength of the plate. So least value of these four will provide you the strength of the joint. So you need to be clear when you are seeing the question. If it is asked strength of the bolt, you need to see either the least value of shear or bearing. If it is asked the strength of the joint, then you should go for either shear strength of the bolt or bearing strength of the bolt or tensile strength of the plate. So in this question it is asked, determine the strength of 20 mm diameter bolt, which means we need to find this strength of the bolt, which is least of shear and bearing. So I could write strength of the bolt is least of shear strength of the bolt or bearing strength of the bolt. Is shear strength of the bolt or bearing strength of the bolt. That is your VD, SB and VD. Now we will come to the part 1 of the question, that is determine the strength of the 20 mm diameter bolt of grade 4.6 for the following cases. First one is lap joint. The question is given the main plates are to be joined by 14 mm thick. So if I do a lap joint, I am connecting with a single bolt. The diameter of the bolt used is 20 mm. This D is equal to 20 mm, grade 4.6, and the thickness of the plate being used is 14 mm. Now as we had discussed before, in a lap joint, if I am applying a force like this, then the bolt will be in single shear. That is, the bolt has a tendency to break from here. So I could say that in lap joint, the bolts are in single shear. Bolts are. If you take your IS code, IS 800 2007, you could see in clause number 10.3.3, the shear capacity of the bolt, that is VD SB, is equal to VD Vn SB divided by gamma m, where Vn SB is Fu by root 3 Nn ANB plus Ns ASB. So you need to understand what is this Nn, Ns, ANB, ASB. Fu is the ultimate strength of the bolt. So ultimate strength of the bolt for 4.6 grade bolt, 4 into 100, that is 400 Newton per, so that is known. Now you need to find what is Nn. Nn is the number of shear planes with thread intersecting the shear plane. So if I am drawing a bolt like this, there will be a threaded portion. Definitely there will be a threaded portion. There will be some threaded portion. This portion is called as threaded portion, and the other portion is called as shank. As you have seen before, when you have studied the parts of a bolt and you have done an assignment on that. This diameter is given as 20 mm, that is the nominal diameter or bolt diameter, that is present at the shank area. Now this portion is called as the threaded area. So if the plane cuts over here, then I could say that it is being cut at the threaded area. And the plane cuts over here, that is, if the bolt becomes two parts over here, then I could say that it is the shank area. So Nn means the number of shear planes with threaded intersecting the shear plane, that is, how many shear planes are present over here. It represents how many shear planes are present over the threaded area, as well as Ns means number of shear planes without thread intersecting the shear plane. That is, Ns represents the number of planes at the shank. So when I am taking a cross section, when I am taking a bolt, always a plane will be cut, minimum one plane will be cut at the threaded portion, because it is having area somewhat lesser than the shank area. Since there are graduations like this, there definitely the area, that is the nominal diameter, the area corresponding to the shank, will be somewhat higher than the area corresponding to the thread. So the cut or the shear failure will occur at the smaller area, that is the threaded area, rather than the shank area. So minimum one plane will be cut over here. So I could say in a lap joint here, the shear plane will get cut at the threaded portion. So I could say Nn is equal to 1, and here there is no Ns, that is, I could say Ns is equal to 0. Ns is equal to 0. Hope you have understood this, how this came like this. This I could write Nn is equal to 1 because it get cut at the threaded portion, and Ns is equal to 0 because there is no second plane or no other plane in case of a lap joint. So now I hope Nn, Fu, Nn and Ns are clear. Now ASB is the nominal plane shank area of the bolt. That is, the shank diameter is 20 mm. So I could write shank area ASB is equal to pi by 4 into d square. That is pi by 4 into 20 square. Now definitely the area at the threaded portion will be lesser than that shank. So the IS code specifies an empirical formula, that is A and B. I could write it as 0.78 times ASB. That is, I could write here, this is A and B is equal to 0.78 times pi by 4 into 20 square. That I'll get it as 245. And ASB and A and B are clear. So this formula you will get the value for VNB, VNSB. You will get the value for VNSB. So VNSB is equal to Fu, that is 400 divided by root 3. Nn is 1 into A and B, that is 240. Here Ns is what? Ns is 0, so there is no term. Now you know VDSB is equal to, that is shear strength, VNSB divided by gamma MB value. You will get it. Table number 5. If you take table number 5, you could see the partial safety factor for material, gamma M for material. In this, the resistance of connection, if it is bolt friction type, that is HSFG bolt bearing type gamma MB, is gamma MB. For shop fabrication is 1.25 and for field fabrication is 1.25. So here from table number 5 was IS for 800 2007, you'll get the value for gamma MB as 1.25. If we get the VDSB as VNSB divided by gamma, you'll get this value as 45.26 kilonewton. That is, the shear strength of the bolt is 45.26. Now the next one is to determine the bearing strength of the bolt. IS 800 2007. If you take clause number 10.3.4, you could see VDPB is equal to VNPB divided by gamma MB, where VNPB is equal to 2.5 kbdtfu. We will see each term one by one. Here kb is the least value of, is the smaller of E by 3d0 or P by 3d0 25 FUB divided by FU or 1. So first you need to understand what is this E. It is written E is an end and P is the pitch distance of the fastener along the bearing direction. Since in this question it is not given, we can take E as given as the least condition given. So if you take IS 800 2007 in clause number 10.2.4.2, you could see minimum edge and end distance from the center of any hole to the nearest edge of the plate shall not be less than 1.7 times the hole diameter in case of a shear or hand flame cut edges. We'll see here sheared or hand flame cut edges because we will not go into rolled or machine cut. So which means the minimum edge or end distance is 1.7 times the hole diameter. It's not written the nominal diameter, it is written the hole diameter. So I denote this hole diameter as D naught, which means I could write E, the edge distance I am denoting as E. E is equal to 1.7 D naught, where D naught is the hole diameter. So the IS 800 2007 gives you the hole diameter, that is 20 mm diameter bolt. If I put 20 mm hole, it won't go through. So we need to have some clearance for your hole. That is 1 or 2 mm higher will be given for the hole such that the 20 mm diameter will easily go through that hole. Table number 9 of your IS 800 2007, the clearance for the fasteners holes for nominal size, that is the diameter of the hole, from 12 to 14 mm. The standard clearance in diameter and width of the slot is 1 mm. From 16 to 22 it is, 16 to 24 it is 2 mm. 16 to 24 it is 2 mm and larger than 24 it is 3 mm. That is, for every 12 to 14 mm diameter bolt we will provide 1 mm clearance, and for 16 to 24 we will provide 2 mm clearance. So I could write here D naught is equal to nominal diameter D plus clearance. That is, for 20 mm diameter bolt I could write D naught is equal to 20 plus 2, that is 22 mm. That is, I could write ES 1.7 D naught by 3 D naught. 1.7 by 3, you'll get this value as 0.56. Now KB is the least value of P by 3 D0 minus 0.25, where P is the pitch distance. P is the pitch distance. Again, if you take here IS 800 2007, you could see in clause number 10.2.2, the distance between the center of fasteners shall not be less than, center of the fasteners means what? That is, a pitch shall not be less than 2.5 times the nominal diameter of the fastener. That is, I could write the small p pitch is equal to 2.5. It is given nominal diameter, that is D. We should write it as D. D is the nominal diameter and D naught is the hole diameter. So this 2.5 D, the minimum pitch is 2.5 D. As I could write this one as 2.5 D by 3 D0 25. 20 mm, 20 plus 2, that is 20 plus 2, that is 22. We'll get this value as 0.507. Now the third one is KB must be the least of FUB divided by FU, where FUB is the ultimate tensile strength of the bolt and FU is the ultimate tensile strength of the plate. So you know FUB is what? For a 4.6 grade bolt, FUB is 400, and FU for 410 grade, FE 410 grade steel is 410. So you'll get this value as 400 by 410.97 or 1. So I could take here the KB is equal to the least of these four, that is I could take the KB as value as KB is equal to 0.507. The second one, that is D. D here is the nominal diameter of the bolt, so I could write this D as D is equal to 20 mm. Now T is the thickness of the smallest plate. This here we are connecting 14 mm plates. If it was 14 mm and 10 mm, we should take T as 10 mm. Take T as 14 mm. And FU is equal to 410. And gamma MB value for determining this you will get it from table number 5. So this gamma MB value you get it at 1.25. So substituting these value, you'll get the value for VDPB. VDPB is equal to VNPB divided by gamma MB. VNPB divided by gamma MB, that is VNPB, that is 2.5 KB TTFU divided by gamma MB. This I could write it as 2.5. KB is 0.507, D is 20, T is 14, FU is 410 divided by gamma MB is, you will get this value 114.8 kN. So for a lap joint, the shear you got it as 45.26, bearing strength you got it as 114.8. When the load reaches 45, the bolt fails in shear. So the strength of the bolt is 45.26 kN in case it is joined by a lap joint. Now see the second part of the question. Determine the strength of the bolt when it is joined by a single cover butt joint with 10 mm thick cover plate. So if you are drawing connection diagram, I have two plates of 14 mm thick. This is 14 mm thick. It is connected by a single cover butt joint of 10 mm thick. It is connected by a 10 mm thick cover plate. So you will see the connection arrangement like this. You need to strength of the bolt here. Here also you can see there will be single shear and bearing. Considering the thickness for bearing will be the minimum of aggregate thickness of the cover plate and minimum thickness of the main plate to be joined. So here I will say when you are calculating VDSB, it will be same as that of lap joint. I am taking VDPB, it will be the thickness will be reduced because here the cover plate being used is 10 mm. So you could write the strength of the bolt in shear here is VDSB NSB divided by gamma MB. Here also you could see there is only one shear plane cutting, and there is only one shear plane. When I am applying a force like this, if this gets cut, what happens? This particular plate will fail, and as a result I could say that connection fails. Here I could write first one, that the shear strength of the bolt is VNSB divided by gamma MB. That is, I could write VNSB is equal to FU divided by root 3 ASB. Here FU is same as before. There's only one plane, A and B, that is the area of the threaded region, that is 0.78 times ASB. Here NS is 0, so you'll get this the same value as before, and gamma MB is 1.25, so you'll get the value for VDSB as 45.26 kN, same as before. Now coming to the bearing strength of the bolt, I could write bearing strength of VDPB is equal to VN, that is VNPB is equal to FU, where KB is equal to, won't be any change, so you will get this value for KB as, so the least of these you will get the value of KB as 0.50. D is also same as before. Now the change here is T, because T is the thickness of the smallest plate, either the main plate or the sum of the thickness of your cover plate. Here, since it is a single cover butt joint, sum of the thickness of the cover plate I could take it as it is the least of smaller main plate or sum of the thickness of cover plates. So the cover plates here, since this is a single cover butt joint, we take the T as 10 mm. Here the NPB value will change 0.5 into 20 into 10 into 410, and your VDPB will be VNPB divided by gamma MB. You'll get this value as 82 kilonewton. So the strength of the bolt is least of your shear strength and bearing strength. Least of your shear strength, that is 45.2 kilonewton, 82 kilonewton, which means the strength here again, when the shear strength reaches 45, or when the shear strength reaches 45, it fails. It won't go up to 82. The bolt will fail in shear. So I could write that the strength of the bolt is 45.2 kilonewton. We'll see the third case. Now we'll see the third case, that is double. The 14 mm plates are used, covered by a double cover butt joint, or it is being joined by a double covered butt joint of 8 mm thick, using 8 mm thick cover plates. So if I draw the diagram, so here first one, that is to determine the shear strength of the bolt. I could write VDSB is equal to, here you could see, in order for the failure to take place, there should be two shear planes, like there should be two cut here, then only the failure of this plate will take place. So the shear plane here for a double cover butt joint is 2. So I could say here either the NN value, that is the number of thread plane, is 1 is here, definitely 1 will be here, and sometimes 1 will be here. That is, if the portion is not threaded, then the portion will be shanked, but definitely one portion will be a threaded area and one portion will be shank area, or a two portion can be what? Threaded area. That is, I could write, there are two options. That is, I could write NN is equal to 1 and NS is equal to 1. That is, one area will be threaded, and the other area will be shank. Or I could write NN is equal to 2 and NS is equal to 0. But never ever NS will be 2, because definitely NN is the weaker portion, the threaded area is the weaker portion, so it will definitely get cut at what? It will definitely get cut at the threaded area. So I could write it, this should clearly define where NN is equal to 1 or NS is equal to 1 and NN is equal to 2 or NS is equal to 0. So in this problem I will be taking N is equal to 2 and NS is equal to 0, so that I could write VDSB is equal to 1. I will choose this one, that is VDSB is equal to FU by root 3. N I will take it as 2 into A and B, that is 0.78 times pi by 4 into 20 square, plus NS I will consider as 0. So I will get this value as 90.53 kilonewton. Coming to, that is the shear strength of the bolt, you will get it as 90.53. Now coming to the bearing strength, that is VDPB. So VNPB is KB dt. KB is similar to what we had done before. KB I could write it as, there is no change in case of what your KB. I'll get this as least of, and this as 0.5. Now D also it is same, but T here I need to write it as T is equal to smaller of 14 mm, because this is 14 mm and this is 8 mm. So either smaller of 8 plus 8, that is summation of thickness of this cover plates 8 plus 8, or 14 mm, that is smaller of 16 or 14. So I could write it as TS 14 mm. I'll take TS 14 mm. So I'll get this value for VDPB as 114.8 kN. The shear strength in double curve butt joint is 90.53 and bearing strength is 114.8, which means that again the bolt strength will be lesser of these two, that is 90.53 kilonewton. So this is what and bolt video. Next lecture we will see the how to find the efficiency of a bolted connection as well as the strength of a bolted connection. So hope you have understood this. Thank you very much.